Welcome to Unlocking Science. Our goal is to glorify God by studying and unlocking the secrets of His amazing creation. I'm your host, Mr. Patterson, but you can just call me Mr. P. And I'm joined today on our program where we're going to be discussing weather and pressure systems by Dr. Jennifer Rivera. Now, we are a live science program, and we're coming to you through the summer months at 2 o'clock Eastern Time. And we want to be engaging with you and interacting with you. So if you want to follow along on Ken Ham's Facebook page, you can find the video for this Unlocking Science episode. And Dr. Rivera is going to be following along with the comments. And as you have questions, we'll answer them. So we love, especially for you kids, give us your name and your age, and we'll announce your question and try and engage with you. And then if we don't have time to get to them on the show, I always try to go back and answer some of those questions in the Facebook comments as well. So keep an eye out for that. All right, today our topic is weather and storms. I think we titled it Weathering the Storm. So when we think about weather, the pressure that's involved in weather systems is one of the key ideas that we want to try and understand. Okay, so when we think about pressure, we think about the density of the air, the temperature of the air, the volume of different air masses. All these things are key principles that we have to understand. Now, when we're studying weather, our big science word of the day is meteorology. Okay, meteorology. A lot of people are having trouble with those big words. So meteorology is not just the study of meteors, but it's the study of everything that goes on up in the sky. And for us, we've come to understand meteorology as the study of weather. So if you watch the weather forecast on your local news channel, the people up there giving the presentations talking about the weather, those are meteorologists, and they're trained to understand weather patterns and all of those things. And when we think about weather, just like we think about with a lot of God's different creations, these things are very complex patterns. So we're going to be talking about some basic ideas, giving you some basic principles, and there's always more for you to dive into and study and understand. All right, have we got people joining us in?
We do,
and
Joshua
channel?
gave a special hi to Claude.
Oh, Claude.
Yes.
Claude's hiding back here.
Yes,
Claude
yes.
is my pet lobster, for those of you who are new viewers with us, joining in for this second season.
Stephanie said he looks like a spider right now.
He's lurking back there in the background. So fun thing for you guys to try and find Claude in every episode. He'll be hiding out somewhere. Sometimes he makes special appearances, like flying on rockets or getting stuck in ice trays and things like that. Okay, so when we think about the concept of weather and pressure, we're thinking about how all of these pieces relate together. Now, the units and the way that we talk about air pressure are a little bit challenging. So if you think about this balloon, if this balloon were the Earth, okay, there's an atmosphere that's an invisible circle around the outside of the Earth all the way around, because the gravity of the Earth, which is a sphere basically, is pulling that air down toward the surface of the Earth. So the higher you are up in the atmosphere, the less air pressure there is. So if I were 3 inches above the Earth in this model, there might be 1 unit of pressure. If I come down here to the bottom, there might be 10 units of pressure. So the air pressure increases as we get closer to the surface of the Earth because there's more air above us. Okay, you might think of this if you've ever gone into a swimming pool and you go down under the water. The pressure gets more and more the deeper that you go. And you might feel that pressure pushing in on your ears, and it's harder, your lungs start to squeeze because all that water is pressing in. Now, it's easy to see water because we can see it, but air we can't see. It's floating all around us and we just can't see it. But air does have a pressure associated with it because it's matter. And matter is anything that has mass and takes up space. So that air is being pulled down, the matter is being pulled down by gravity. Okay? So all of those things have to do with air pressure, and how we measure air pressure is using a structure called a barometer. So here's how this was first discovered. Scientists back in the 1600s noticed that if they would fill a dish like this and fill this tube clear up to the top with a liquid, that part of this liquid would fall back down, and there was liquid in the tray, and then there was liquid up this column. And it always sat at the same height. And this was a repeatable, observable phenomenon that these scientists noticed. And when different scientists studied this, people you might know like Galileo, they thought that vacuums that were created didn't have any matter in them, but that matter around them would flow back into it, so that there was some matter there. But then one of Galileo's students by the name of Torricelli, he came up with the idea that there is absolutely no matter inside of the vacuum. And the vacuum was actually totally devoid of any matter. And the liquids that they used were water initially, but then they changed to mercury, which is more dense. Now, the different heights that the water or the mercury filled the column could be measured directly, and that became what we know as a barometer. And one of the units that we use to measure pressure is named after Evangelista Torricelli, and it's called a torr. And a torr unit is one of the measures of pressure that we use today. Any questions coming in yet?
Not so far, but someone said that you are the best science teacher they've ever had.
Oh, thank
so
you.
I thought you would enjoy
I hope
that.
I'm not the only one.
Yes, yes. And one comment was made, this is why when you're in the mountains your ears pop and why water takes longer to boil.
Absolutely. So
Air
if
pressure.
you've ever lived in an area where there are mountains, so I grew up out west where we're in Kentucky right now, and I think the elevation's about 700 feet above sea level. I grew up out west and we had mountains that were over 10,000 feet. So you'd buy a bag of chips down in town where the air pressure was a certain level because you had this much air above you. And when you drive up the mountain and there's less air pressure, the bags of chips would explode in the back of your car while you're driving up the mountain because of the difference in pressure that was happening there. So yeah, and they make your ears pop. If you've ever driven up or down a mountain range, you can feel that pressure difference inside of your ears wants to balance with the pressure outside. So thankfully, God has given us eustachian tubes, little air bypasses back in the back of our throat that help balance out that pressure. Okay, you guys have probably all seen a map that looks something like this, probably on a news broadcast, trying to look at the weather and those types of things. And this map, you'll notice, has all of these little different lines and circles and bars and symbols. And the L's that you see here on the map, if I can find one over here, this little L and then these H's, these stand for different pressure systems. So low pressure systems and high pressure systems. Ribbons that you can see with the different triangles, and then the red ones have little ovals on them. Those are what we call fronts. And a front is where two different weather systems are interacting with one another. And fronts are what really determine our weather. So here in Kentucky, yesterday, it was a beautiful sunny day. We had what we would call a high pressure system. I didn't see a single cloud in the sky until in the afternoon when this low pressure system moved in. Right? So if we think about low pressure and high pressure systems like we see on these maps, we can visualize them with some of these circles here. So if we think about the layer of the air that's closest to the surface of the Earth in the atmosphere, there are these different air masses. So let's say this red air mass represents a hot air mass. It's got a lot of heat in it. And this blue one represents a cold air mass. Now, if this warm air mass were sitting here and this cold air mass was moving because there was some force of wind pushing it toward it, where the cold and the hot meet, that's what we call a front. So this little line that we would get if we held these two together like this creates a front. Now, if you've been with us when we've talked about density before, you'll know that temperature influences the density of a gas. If a gas is warmer and the temperature is higher, then it will be less dense. And things that are less dense tend to float or to rise compared to things that are more dense. So if this cold air is fairly dense and this is less dense, when these two fronts, when this comes together at this front, the hot air is going to tend to rise and it's going to push it up and create this little frontal system. You may have seen that, especially if you live in a plains area or somewhere where you can see out over a long distance that's flat. you'll almost see a little wedge up in the sky where a line of clouds starts to form. So as this hot air that's holding moisture starts to rise up higher in the atmosphere, it cools and produces clouds. And then along this front, we get rain as a result of those clouds. So today, if you could look out the window here, it's kind of a rainy, drizzly day. We woke up to that this morning because this frontal system had moved in, and this cold front came in, brought that cold air, and it condenses that moisture in the air and forms the clouds and causes it to rain. And that's moving through the area. And right now, we've got a high pressure system behind it that's moving. So there's always this constant balance of high pressure and low pressure and cold air and hot air moving in all kinds of different ways. And it's really challenging to try and figure out how all those pieces are working together.
Yes, we do have one question from Carol. I get a huge headache and can tell that a storm is coming. Is that high pressure or low pressure?
Anytime you have a change in pressure, some people can feel these things. Some people are sensitive to that and they'll get headaches or migraines induced by pressure changes. Some people can actually feel it in their joints, and we think what that is there's tiny little gas bubbles inside of the joints and the cartilage, and as that expands, that creates pressure and causes pain inside the joints. So if your grandma ever told you her knee starts hurting when it's going to storm, that's a real phenomenon, and people can actually predict those things based on their bodies. So your knee can predict the weather.
And you almost touched on this question, but it's come up a few times, and that is, why do weather people get so many things wrong? And you kind of mentioned about all the variables in place, right? That's one of the reasons.
All of the variables, if you could think about all of the different directions that air masses are moving during a storm front coming in and out over a huge area. So if you had to predict where this frontal line right here was going to go based on movements, so it's in Georgia, but the air up here in South Dakota and even into Canada is going to be influencing that. There's upper atmosphere, lower atmosphere phenomena. There's cooling and heating happening at the surface. Things over water cool and heat differently than things over land. The color of the soil and all of those things can influence all of the different weather patterns. So there are literally thousands of variables that go into trying to predict the weather and understand how all these pieces work. So this goes to our concept of observational versus historical science. We can take all kinds of different measurements with barometers and temperature gauges and wind meters called anemometers, and use Doppler radar to look at different wind directions in different areas. All of those things are done in operational mode, and we can see those things and repeat them. Everybody can agree. But predicting them into the future or looking back into the past, that's historical science. That's a different type of thinking and a different way we apply science. Okay, let's move into some of all these contraptions that I've got sitting around back here. All right, so what I've done here is I've built a whole bunch of different models of barometers. So Torricelli built this first barometer using mercury, which is kind of a toxic metal, and we don't like to play with mercury a lot anymore. And mercury worked well because it made a column that was only about 29 inches tall, 30 inches tall, to be able to measure the air pressure, where the water columns that they would use had to be over 30 feet. If you had to take that with you, you'd probably want to take the 30-inch one over the 30-foot long one.
Yes.
Okay? So very different in size. So mercury is very dense. And he made these barometers that would measure that pressure difference in the air. So basically, if we think about this model here is called a dry barometer. So what I did to construct this, and this is an activity we're going to do on our hands-on science segment that will be airing on Friday. So we'll give you some more information about that. So what we have here is a jar, and I put this together yesterday when we had a nice high pressure system. I stretched a balloon over the top of here and double rubber banded it to seal in the air that's inside of the jar. So the pressure inside the jar represents the air pressure yesterday, and the pressure outside the jar represents the pressure today. So right now, if you could look at this needle really carefully and closely, I made that long pencil line yesterday, the one that's just above the pointer, when the pressure was high. This morning, in the middle of the storm, the darker line that you see down below the pointer, that's where the pressure was this morning. And right now, it's kind of in between. So here's what's happening. If we think about the air pushing down on top of this yesterday, the pressure inside the bottle would have been balanced with the pressure outside the bottle. Okay? And today, there is a low pressure system in our area, so there's less air pushing down, and so the air inside is going to push up. So the balloon is actually making a very slight dome. So if I take my pointer and I make a dome with it, it's going to tip it down away from here if the pressure is lower. So the pointer goes low in a low pressure system. And if the pressure up here is higher than the pressure inside the jar, it's going to push down on the middle more, and the pointer is going to go up. Okay? That's a little bouncy there. Okay? So this is called a dry barometer, and it can tell us relative pressures. So compared to yesterday, I can tell you where that was at. The pressure yesterday was about 30.06 millimeters of mercury, and this morning it was like 29.8 in that low position. Okay? So this type of barometer is called a dry barometer. Any other questions coming in yet?
One question is, are animals affected by weather? That's from Sarah.
Oh, yes. Animals, especially mammals who have ear systems just like us, they would be affected by the pressure changes and those types of things. I don't know if deer can predict the weather based on those things, but we do know that animals have amazing senses that God's given them beyond what we have to be able to understand those things. Mm-hmm. And they'll often sense when pressure systems are changing. Even fishing can change. People will forecast fishing based on the pressure systems that are moving in. So yeah, animals are affected by these weather and pressure systems as well. Okay, here's another example of a wet barometer. This one's a little less technical to make. All I've got here is a glass jar on the bottom and a glass jar on the top, and I've filled them up with liquid. So what's happening here is you can see that the water level inside of the top jar is much higher than the water level down here, but the mouth of the bottom jar is down underneath the water surface. So the water surface is up here. This is open around the rim of this jar so that air can push down on the surface of this water. So all the air that's pushing down on the surface of this water is forcing the water inside the jar up into this other jar. So if we were under a higher pressure system, so tomorrow, if I were to draw a line across here, and tomorrow it was a bright, sunny, high pressure day, I would expect the water level in the top jar to go up. If it were a lower pressure system tomorrow, I'd expect the pressure or the water to go down because there's less air pressure pushing down on the water in the bottom jar. So this is called a wet barometer. This is basically the model of Torricelli that he used to make that.
Now, someone asked, why was the previous barometer called a dry barometer?
This is a dry barometer because I've just got dry air inside of here. So I'm using a dry membrane, which is just a latex balloon, to create this pressure sensor. This one is using wet. It's got the water inside of it. This is another style of dry barometer. This is the other, or wet barometer, sorry, that we're going to make. So you'll notice I've got the cap on here loose so that the pressure of the air can push down on the surface of the water here, and it's going to force the water up the tube, and I've drawn up a little water into here, and I can actually see that the water is forcing up the tube and it's sitting at this level. Again, if we get into a high pressure situation tomorrow, I would expect this line of water to move up the column, and if we get into a low pressure system, I'd expect it to move down. And I've drawn some marks on here so I can measure that and track that. And you can actually keep a weather log and compare those things to the actual air pressure and the barometer readings.
Someone asked if plants can show us when it's going to rain.
I don't know the answer to that question, and I'm not afraid to say that. There's a great science lesson. If you don't know the answer to something, don't be afraid to say so. I'm sure that there are some ways that we can look at plants and determine whether they're opening. They have little pores underneath them called stomata that regulate the water and airflow inside and outside the plant. There might be something to do with that, but I really don't know the answer to that question. That is a great question, and I hope you'll go find the answer, and maybe you can post it back in the comments for us later. So let me demonstrate to you with this bottle what's going on in this system. So I've put some red colored water down here inside of this part, and I've put some blue colored water up here in the tube up at the top. Now, if I were to add pressure to this space up here, if I were to compress this air, that would push this water down, the red water, which would force the blue water up the tube, and we should be able to see, if we can focus the camera right on this spot, when I press on the water, you can see that goes up just a little bit, up and down. So the more pressure that I have on the surface of the water, the higher it will rise in the tube. But you notice that wasn't a very big change. That's why mercury makes a better thermometer, or a better barometer, than water does. Absolutely. And here's one last type of barometer that I've made. This one is open on this end, and I've filled this one, rather than water, with mineral oil. Because if I leave this sitting out with water in it, it's going to evaporate, and then the level of my barometer is going to not read accurately. So I've filled this with mineral oil, and I've put a little drop of food coloring, which sank a little bit down here, and you can see the level of the oil is right here. So again, if there were higher pressure pushing down on this little surface over here, I'd expect this bubble to go up, and if it were lower pressure tomorrow, I'd expect the bubble to go down. And that's important because we can use that to predict the weather and how it's going to change. If a low pressure system is moving in and the barometer is falling, I would expect the weather that's coming up to be cloudy and rainy. If it's high pressure and it's increasing, I'd expect the future weather to be warm and sunny and not as many clouds.
There was one question about a wall barometer. Okay. Levi said he uses an analog dial and needle to tell barometric pressure. How do those work compared to the units that you made?
That is called an aneroid barometer, and it basically works pretty much the same as this little jar does. So inside of that barometer that you may have mounted on your wall is a little cylinder like this, and it's filled with air, and it's got little segments that allow it to squeeze together like an accordion. So accordion, to me, it's one of the best barometers out there. Oh, terrible joke, sorry, couldn't help it. So when that little cell, if it's higher pressure, that squeezes the air inside of that cell and it compresses together, and there's a little needle attached to it, and that needle will move, and it's set off on a lever so it moves different directions. And if the pressure outside goes down, the needle will drop, and that measures the pressure. So if we think about standard pressure, we talk about that in chemistry and physics. We want to do things at standard temperature and pressure. This is my little cheat sheet so I don't forget all the numbers. Okay? If we think about our distance above the Earth, at sea level, so if you were right here on the surface of the Earth and the atmosphere were this high, then that standard atmospheric pressure we call 1 atmosphere is one way to talk about it. That's equivalent to a column of 760 millimeters of mercury, or more commonly in America we use inches, so 29.92 millimeters of mercury. So if we had that test tube setup that I had earlier, we'd have a column of mercury that would rise 29.92 millimeters, or inches of mercury. And then we can measure the change from that. So most of those barometers that you'll look at on the wall usually go from somewhere around 27.5 up to 31 or so, so that we can look at that pressure change inside of there. Other units, we use torr, millimeters of mercury, kilopascals, bars. There are lots of different units, especially as physicists do these things in different ways. Okay, let's try and demonstrate this for you in a very dramatic fashion. So let's say we were in the middle of a hurricane, which is an amazingly low pressure system. Right? So this jar is going to simulate the low pressure that we'd experience inside of a storm like a hurricane or a tornado. So this is set up with a vacuum pump, and it's going to vacuum the air out of here. Now what I expect to happen, and I haven't tested this because I didn't want to blow up my barometer, but when I turn on the switch, it's going to pump air out of here, so the air inside of the jar will be high pressure. The air inside the bell of this will be low pressure. Everything in nature likes to move from high to low. That's what creates the winds around us, things moving from high pressure, air moving from high to low pressure, and then different angles that it all moves. So I'm going to turn this on. If we can bring the camera in, we're going to try and get right down here at the level of this membrane, and I hope we're going to see that needle go way down, and you should see the top of that balloon start to bulge up. Let's see if it works. Did you see that? Okay, so that went up so quickly that it was a radically different change. So that bulge, you can see that needle, and when it comes back to a balanced pressure, the needle is actually going to, right there, it hits the edge of the jar, and it'll actually start rising from that point on.
Mr. Patterson, someone said your safety goggles should be on.
This is a pretty secure container. I'm not worried about that. The next thing we're going to be doing is going to require us some safety glasses. Okay, so let's go ahead and put our safety glasses on. Now, we talked about cloud formation a little bit earlier. There are several different ways that clouds form in weather systems, but one of them is what we call adiabatic cooling. So if you've ever been out in the plains or an area where you can see a lake off in the distance, you'll often notice that in the afternoon in the summer, a giant cloud will form over the top of big lakes. That's because the sun's energy is evaporating the water, and as it rises, there's less pressure up in the upper atmosphere where the cloud is at, and it's a little bit cooler. And so that allows the gases to expand and cool, and they give off heat in that evaporative cooling, and they form a giant cloud. And there was a lake where I lived in Wyoming called Lake DeSmet, and every afternoon a big cloud would form over it, and then you might even get a little rainstorm out of that cloud. So that lake created its own weather system. So I'm going to make a cloud inside this bottle. Okay, so what we're going to do is we're going to represent a high pressure system by adding pressure into this jar. So I've taken a regular jar of sports drink, and I've drilled a hole in it and put in a valve from a tire, and I'm going to pump air. I'm going to stand up for this though. I'm going to pump 13 pumps. $11, $12, $13. All right. Now I'm going to open this bottle very rapidly, and what's going to happen is the air is going to, the pressure difference is going to change. So we're going from high to low. As that happens, the vapor that's inside of here is going to condense very rapidly. Okay, 3, 2, 1.
Ooh!
We lost the cap right on my fingers. That's why we put on our safety glasses. And you can see that cloud formed, that vapor formed, and that's the same thing that happens when that vapor rises up into the atmosphere and it cools and condenses. All right, so we've gone over a lot of basic ideas about weather, tons of different things, different aspects of weather. Again, it's so much more complicated than we could ever explain in one little episode, but there's amazing things that God's made to help stabilize the weather systems in our planet, and we know that we can trust Him, that His character is reflected in the way He's created His world, and we can trust that weather's going to be a common thing for us until the end of time, until he brings about the consummation of all things. Any final questions we can answer there?
There was one question about air pressure in planes. Like, how do they accommodate for that air pressure when they build planes?
So when they build an airplane, as they go up in the atmosphere, let's say you're flying at 30,000 feet, that would be a very low pressure environment. So the air inside of the plane would want to try and escape out of that, because it's higher pressure on the ground. You fly up in the air and it would go out. So they actually have to pressurize the cabin, and you'll hear them say if we have a low pressure event, so if too much pressure escapes from inside the cabin to the out, then the oxygen mass will come down and to provide you with oxygen. So they have to build an airplane in such a way that it can pressurize that cabin if it's going to be flying at high altitudes to protect us that way.
Which is usually why, too, you have to pop your ears to
Yes,
stabilize
again,
that pressure.
they're pressurizing the cabin and stabilizing all those things. All right, we thank you guys for joining us again for this broadcast of Unlocking Science. And all of these episodes are going to be on our new platform, answers.tv. So we would love for you to go there and check those things out. You can see this show live. You can see past episodes of this and lots of other AIG produced materials there on answers.tv. So please check that out. Get a subscription for your family. And until then, I pray that you would get out and enjoy all of God's amazing creation.